Okay, thanks a lot. I guess I'm ready. Welcome from my side. It's a pleasure for me to be here and to give you an overview on the digital calibration certificate, which we established in our accredited calibration laboratory at BAM. So we are the Federal Institute for Materials Research and Testing. I changed the title a little bit, but the topic is still the same. And so I want to present a deeper insight into this DCC. First of all, I want to talk about the general information on the calibration and metrological traceability, and then we will check a calibration certificate and what's actually inside it, so the value it bears, and this is then already the motivation and transition to the digital representation of this certificate. I would like to address more specifically you as the user of such a calibration certificate, although I'm representing a calibration laboratory, so we are the ones who issue it, but the actual added value is given at the receiving side of it. So that's why I want to address this a bit more. All right, let's get started. Maybe you are familiar with this representation of the calibration pyramid, which is about a sensor or test device in use in a company, for example, to monitor a production process, and this is being calibrated. Calibration always is a comparison between the measurement of this device and a reference in order to evaluate the accuracy and precision of it. And the results of this measurement is provided in form of a calibration certificate that is provided to the user of the device. However, also the reference needs to have a known accuracy and precision, and so this reference also needs to be calibrated. This is usually done in an accredited calibration lab, which also issues a calibration certificate, and also these labs need to have traceability, and usually they are linked directly to the national normals, which are hosted in the National Metrology Institute. So these are the ones who provide the units on a national level and pass them on to the labs also in the form of a calibration certificate. So if you have an uninterrupted chain of valid calibrations from the national normal down to the test device, which is documented by the calibration certificates, then you are able to receive the metrological traceability of the measurement results you are having and you are using in your facilities. This, however, can only be done if the calibration certificates and the data it contains is processed in a proper way, because, for example, the measurement uncertainty is passed on from top to bottom, and on each step further contributions to this measurement uncertainty have to be made, so the uncertainty actually rises from top to the bottom. And the final uncertainty that you can use depends on your measuring task, on the conditions you are measuring, and on the quality management in use. So as you see, the calibration certificates are an important feat where the quality management stands on. So let's check in more detail what is a calibration certificate. So this is the human readable representation that you probably all know. It contains information on who calibrated, what was calibrated, when was calibrated, and so on and so on. So I have an important question for you. What are you doing when you receive a calibration certificate? That's a very important question. I want you to think about it for a moment. The most important message here, that a calibration certificate is not just a demonstration document. It contains a lot of valuable data, and you paid for this data. You paid for the calibration, and the calibration lab puts a lot of effort into getting this data, and so you should use the data properly in order to take out the advantages of it. And I want to explain this a little bit more in detail. Of course, most of the important data is shown in the final result of the calibration, usually presented in the form of a table. This is an example of a PT100 thermometer calibration, and you see on the very left side we have the temperatures of the reference from our laboratory, then we have the temperatures from your device in calibration, then we have the deviation, which is just the difference between the two, and we have the measurement uncertainty. And if we want to talk about how to use this data, we need to talk about measurement uncertainty, of course. The measurement uncertainty is a measure of the precision of this device. And here's another important message. The measurement uncertainty that you are using in the process and that you have to consider in terms of metrological traceability is not simply the measurement uncertainty that is provided here in this table. Further contributions have to be added, as I mentioned before. And the first further contribution is just in the column on the left side, it's the deviation. The deviation is a measure of the accuracy, so it gives the offset of the results from the actual quantity that you want to measure. So it's also in English regarded as the measurement error. So this you have to take into account, and in the easiest case, you simply add it to the uncertainty. However, if you take a look, you can realize that sometimes the deviation can be a major impact. It can be a dominant factor in this, and this, of course, you don't want to have. If you add simply the two together, you have to make sure that this still is in line with the requirements of your management system. But if it's not, there is an easy way to tackle this. You can make a correction. You can just relate the measurement values to the reference values and define a correction function that you use to correct each single measurement value. And in this way, you increase the accuracy of your results, and you reduce the uncertainty that you have to take into account. However, you cannot completely get rid of it, because as you can see, there is some remaining deviation from your correction function, and this still has to be taken into account. Another contribution you will find regarding further information that you will find in the document. For example, for a PT100 calibration, you can find a sentence like this: the hysteresis of the item can have an additional contribution of 40 millikelvin. This contribution is not included in the measurement uncertainty stated in the table. So you have to take it into account, except for the case that you measure exactly the same way the device was calibrated. You can find information in the certificate how it was calibrated, if it was calibrated with rising temperatures or with falling temperatures, and if you measure it the same way and start at the same temperature, you may not need to take it into account. But that's usually not the case. If you have a process monitoring, you measure temperatures all over, so you need to take into account this further contribution. Another contribution that usually always needs to be taken into account in addition is the long-term behavior, because in the calibration we cannot know about it. A calibration is always just a moment measurement when the device is in our lab, but when it leaves our lab, we don't know what happens with it. So the long-term behavior is something you have to evaluate yourself, actually. And this is done with a device history. If you have many calibrations over several years, so this is one example of one of our voltage standards used in our lab. We have many calibrations over the years, and we can assess the drift of the device over time. And then either you take into account the amount of drift between two calibrations as a measurement uncertainty, or you can also make a correction function and have a daily value, drift-corrected value of your results. But still, in this case, as we had with the measurement deviations, a small fraction will remain in your uncertainty budget. Yeah, further contributions may come from the deviating conditions. So the calibration is usually performed in idealized conditions, very stable temperature and humidity and everything. But that is also usually not the case in use. For example, if the PT100 was calibrated with a current of 1 milliamp and you use it with 10 milliamps, there is self-heating in the device that you have to take into account. And you will find the value of the current in the document as well. And last but not least, the level of confidence. The results in the calibration certificate are usually given with a level of confidence of 95%. You can find this information also in the document. You have to consider if 95% is fine with you, or if this is a very critical value for your process, you maybe want to have 99%, and then you have to increase the measurement uncertainty accordingly. So as you can see, there is a whole colorful bunch of contributions that have to be taken into account, and if you master all these contributions and if you can properly evaluate them, then you can actually take the advantages of these things, because you can be certain about the trueness and precision of your measurement results. And finally, you can also replace specifications from the manufacturer with the uncertainty, which is usually still smaller than the ones that are given in the datasheet, for example. And ultimately also rethink about tolerances and stuff. So there is an actual monetary value in your process if you process these calibration data properly. However, this comes with a cost. Of course, as you may know, this is a lot of effort to master these contributions, and you need a lot of know-how, and I guess that's also the reason why it's not often done. People do it, of course, if they have to do it or if they have a really critical process, but these cons are heavy to some extent. And also you have the risks from manual data transfer and processing, because there are errors can occur which may not be detected so early, and this can cause severe problems. And this is exactly where the DCC comes in. If we have the data from a calibration certificate provided in a machine-readable and machine-interpretable format, we can tackle those cons. We have no effort because everything can be automized. The know-how needs to be there only once when you plan how to use the certificate, and the risk from the data transfer and processing is actually vanished. So we hope that if we can reduce or even get rid of these cons, then everybody can take advantage of these advantages of the calibration data. And that's why we are establishing the DCTs in our lab. PTB has done the major work and the foundation of this together with others. So it's a globally harmonized system. The PTB has created a schema, an XML schema for machine-readable content of calibration certificates. And this makes up the level 3 in this utility model of the machine interpretability of the content in a document. Now we are trying to get to level 4, which means we need to have good practice of these certificates. It means we need to define very specifically for specific processes and specific quantities how information is incorporated into the schema and how it is provided in a DCC. And this makes the machine able to read out and also interpret this data correctly. Let's get some facts about the DCC itself. The DCC is a complete and valid document that contains all necessary information. So actually a human-readable version of it is not longer necessary because it already contains everything. So we can provide a DCC as a standalone document. And it can be issued within accredited and non-accredited bodies. So also accredited labs can use this, and non-accredited labs can use it as well. All automizable information are machine interpretable. This is what we want to tackle with the level 4. That not only the main data, the main measurement data is machine interpretable, but also every single other bit of information to make this automation running. And it can be electronic seals and signatures, which is of course important to protect the data in the document. With such an electronic seal or signature, you can be sure about the data integrity. It cannot be changed. If it's changed, it cannot be validated anymore, so any change will be recognized immediately. And it also authenticates the issuing body of the DCC itself, that not somebody else can come, I am BAM, here is your certificate, and it contains some crap. With the harmonization that we are currently underdoing, we will have interoperability of this DCC, so that a DCC from different issuers can be read, can be assessed with the same software. Let's take a closer look into the XML content to make this a bit more clear. So this is an excerpt of this XML of the DCC. It contains the data of the far left column that I showed in the table. So this is the reference values. We have some human-readable content, so that's important, I guess. If you have a DCC for the first time, you can get an idea where to find what. It also contains timestamps of the measurement. This is, for example, important that a machine also can understand what is the order of measurement values that are recorded. And we have these ref types. So these ref types are the key elements to provide the machine interpretability. Because here, the machine can get the semantic information it needs to interpret this data. We have the temperatures down here, and with the ref type reference value, the algorithm can know, okay, this is the reference value and not the measured value or the deviation. So that's very important for a machine to understand this. Further ref types can provide further semantic information. For example, saying that these values stated here are actually not measured. They are mean values of a bunch of measured values. And these temperatures relate to the ITS-90 scale. So these are important information for the machine interpretability. And we have the digital SI. As I mentioned, this is already incorporated in the DCC. And what is shown here is that you also have the possibility to provide measurement values in different quantities or on different scales. This is, for example, good practice in temperature. Of course, it's good to provide temperatures in Kelvin because that's the SI, and that's used for comparability of values. But of course, also people want to have it in degrees centigrade, for example. And you can give both in parallel using such an SI hybrid architecture. Okay, as I said, we are ready to issue DCCs in our lab, and this is one of the examples. This is a PT100 calibration that is performed according to the DKD R5-1 rule, which we are using in Germany. It is calibrated within our accredited scope. So we had already the approval from our accreditation body to issue DCCs. The DCC was part of an evaluation with our accreditation body, so it was approved. We end up having 850 lines of XML code compared to 3 pages of text when we issue a paper certificate. This DCC is automatically generated in our lab with a software that we wrote ourselves. So we use non-proprietary solutions for this. And it's readily validated against the DCC schema. We are using the most current version of it because the Digital SI just had an update some weeks ago, and this is only incorporated in this newest version, and we are already using some of these novel architectures that the DSI provides us. So DSI is already incorporated. It contains these harmonized bookmarks, these ref types I was talking about. That's very important. And our paper certificates come in German and English language, and so does the DCC. So you can put as many languages as you want inside. And we seal our DCCs using the novel digital accreditation symbol that our accreditation body is providing. So we piloted these accreditation symbols together with DAX. This is not a picture that you put into the DCC, but it's a PKI, it's a public key infrastructure. In principle, what you get is a file, a sealing file, or a certificate file that you can use to seal your XML data. And this gives you all the functionalities of a regular seal, the data integrity and the authentication, and the further functionality of the accreditation validation. Because if the seal is validated by the receiver, which is of course an important step in the process, then the receiver can be certain about the valid accreditation of the issuing body. And together this makes up a so-called e-attestation. This here is, by the way, also usable on PDFs. So a little bit more about the structure of a DCC. So we have the administrative data, which contains information about the schema version it is validated with, the software it was validated from. We have some core data. This is the most important data of when it was calibrated, who calibrated, and where it was calibrated, and also contains unique identifier, which is of course important to handle this certificate digitally. We have information about the item itself, about information about the calibration lab and who was responsible for the calibration. We have the information on the customer, so everything that needs to be in a certificate is incorporated here. And a statement section where you can find statements about how is the traceability, what is the validity range of the calibration, maybe information when it should be recalibrated, and so on and so on. And then we have the results section, which starts with the used methods, or usually this is a link to the method description that is used in calibration. We have the measuring equipments that we are using in our lab, so the reference standards we are using, the influence conditions, and finally the results. I was showing a part of it. And on the very bottom then is the accreditation seal in our case, or an electronic signature if you want to use it like this. Further content can be what we are not using, but which is possible in the DCC architecture, is conformity assessments. We can have information about adjustments, so as found as left calibrations, and also information on corrections, calibration curves, functions, or factors, and so on. And also some comments, which can contain, for example, the raw data or the device history, if it's known to the calibration lab, interpretations, and so on. And the DCC can also contain a human-readable format or human-readable representation of itself incorporated in the XML architecture. So this can be done. An alternative is the translation of the XML to a human-readable document, which is also in principle available. Okay, this is as far as the generation of DCC goes. I quickly want to highlight also the usage of the DCC, what needs to be done, or how the DCC is processed. Of course, you need to have a software that is able to read the DCC and interpret it, and this starts with doing the necessary validation. It should validate the signature in order to take advantage of the functionalities it provides, otherwise it's useless. You can validate also the schema, and maybe you have some own criteria that you want to validate that you can also automate because all the information is machine interpretable. In the future, a validation can be also done in a quality data space that is currently under development at BAM together with PTB, and I will come to this in a moment. With this validated and read out data from the DCC, then you can do the correction of your values from your device and do the handling of the measurement uncertainties that I explained. This can also be fully automated, and then you have a quality assured data from your measurement, and with this quality assured data you can make a quality assured conformity assessment of your process. And everything that is shown here happens by the push of a button, and this is literally. Everything can be automated. We are showing that at our booth. Our booth is just 10 meters down the way. If you want, I invite you to visit us. We can take a deeper look into the DCC, into the source code. I can show the ceiling, and we also demonstrate the usage of the DCC data at the push of a button. The filing finally can be done using, for example, Asset Administrative Shell. There is currently under development a submodel for it. I guess it's to be published very soon, so this can be also incorporated. As I said, as a small outlook, we are developing this data space for quality documents. So this is a federated data exchange platform. All the players for quality assurance can be incorporated, the customers, accreditation bodies, the laboratories, and the manufacturers. And this platform allows to issue, distribute, and trace, and also verify these quality documents, like the DCC, like the digital product password, test reports, and other documents which will be provided in a digital form in the future. So this is just a small outlook. Let me quickly thank my DCC team, which is also present here at the fair, the DCC core team from PTB, which of course did a lot of work into this, which we are lucky to just take over and use. The Deutscher Kalibrierdienst, where this harmonization now is currently going on in several subcommittees, and also the accreditation body DAX for the digital symbol. This work was heavily supported by the initiative QI Digital from the German Ministry for Economics and Climate Affairs. And at the very end, I want to give you a link to our DCC landing page. And on this page, you can find a download of a zip folder. This zip folder contains a complete DCC of a PT100 calibration, a PDF representation of it, and some information how to validate this accreditation symbol on it, which is present on both documents. Thanks a lot for your attention.
Thanks a lot, Michael. So please, questions from the auditorium. So I don't see any question. So I would like to tell it once more what Michael has said. Just go down to this direction about 10 or 15 meters in the middle of the area. There you will find the desk from BAM, where you can look at the DCC and all what they have done, and there you can also ask questions. So thanks a lot. Now we just make a small change, and then we will start in about 5 minutes. Okay.